Okay, thank you. Okay, thank you all for having me here. It's actually quite a great pleasure to see so many people. Also, this is like my first talk in person as a visitor in the last 2 years almost. So it's a mixture of excitement and being intimidated because you're quite a many people here. Also, I almost told Flavio to skip the part that my PhD was in string cosmology because I thought I would lose all of you. But I hope you can stay on board with me as I go along. So before I start, let me say a few disclaimers. As Flavio said, my background was mostly in string cosmology. It's quite recent that I'm getting interested in quantum information and applying that for recovering space-time. So that means that I'm no specialist at all. If anything, I'm here to learn with you because I want to use quantum information to try to put forward or move forward this kind of program. So yeah, if anything, I hope to cause some reactions here. I'm going to make some bold statements, and I hope I have some discussions and something that you can actually bring home with you. Okay, so to keep everyone engaged, I won't be pulling you, but I did this poll back in April in Stockholm. We were in an event called the OKC Day. There was about 40 people more or less. And one of the questions that I asked them was, is gravity a fundamental interaction? And now you can reply yourselves in your mind. And maybe, I mean, you're more or less the same size of the group that I had pulled back then. And this was, yeah. It is fundamental and it is an interaction.
So what do you mean by fundamental?
Yeah, so that you cannot have anything from which gravity emerges. I can explain now when I go over this.
It's an approximation.
Well, I mean, for instance, like you know that Fermi theory is an emergent theory, right? So like there is something which is more fundamental when you talk about pions, right? So in the case of, for instance, people said that gravity is a fundamental interaction, like the majority actually thought so. And you see that some people think that it's not a fundamental interaction, and some people think that it's not an interaction at all. So for instance, if you just think about classical gravity, right? Gravity is just a complicated form of like inertia. There is no interaction whatsoever. But you see that even people who reply that it is a fundamental interaction, if you do any sort of quantum gravity, most models don't take gravity to be fundamental. I mean, string theory, for instance, strings are fundamental, and the gravity emerges as excitations of the string. So it's a bit misleading that actually most people think that gravity is fundamental, even though most theories don't take gravity to be fundamental at the quantum gravity approach. Anyways, the second question that I polled people was, should gravity be quantized? And I guess you should expect that if most people reply that it is a fundamental interaction, most people are going to say that yes, gravity should be quantized. So half of the people more or less. So some people said that gravity shouldn't be quantized, perhaps the people that think that gravity is not a fundamental interaction. So if gravity is emergent, like sound waves, you don't expect to quantize sound waves as well. And some people are like on the fence, kind of like should be or shouldn't be. And although this looks a bit weird, it kind of makes sense when you think that actually you do classical gravity and everything looks like inertia. But when you linearize the theory, you have like a spin 2 particle, the graviton, and you can talk about quantization, for instance. So it's kind of like acceptable that some people are perhaps on the fence about this kind of a question. Anyways, those are, of course, challenging questions and very complicated. So let's now tone down and become much simpler. Let's talk about things that we do understand. And this is something that we do understand, right? So when we talk about Newtonian physics or classical mechanics, things are rather simple. We have a state, usually a point in phase space, and we have an evolution equation, which is Newton's equation. And everyone has a very clear picture of what that means, right? In fact, if you have an operator that can evolve your point in phase space, and you know exactly the state of your universe at a given time, you can actually predict everything that happens towards the past and in the future. Of course, this is the concept behind the Laplace's demon. So classical physics as a whole is quite easy to grasp. Of course, no one ever does that, right? No one is a Laplace demon. And so things that are very relevant that you have to do even in classical physics is to talk about emergent descriptions. We have like stat physics, we have thermodynamics, dynamical systems, or even higher up, we have chemistry, biology, so on and so forth, right? By the way, I thought that my representation of Laplace's demon was accurate until I came to the hotel here next door. And in my bedroom, there was this picture. which is, I guess, a weird demon. And perhaps that's why I didn't sleep so well last night. Anyhow, this is quite simple to understand, and the ontology is not very complicated, I guess you would all agree. But then we have other things. We have things like quantum mechanics, and you open a textbook on quantum mechanics, and everything starts super well. We have a state that now is not a point in phase space anymore, but it's a vector in Hilbert space. And we have an evolution equation, Schroedinger equation. So far, so good, and you see the analogy with classical mechanics. But then suddenly you have a bunch of other stuff. So we have things which are observables, but actually it's not the state. They are given by Hermitian operators in general. Then we have something like the Born rule. So instead of talking about certainties, we talk about probabilities. We don't have the Laplace demon picture anymore in this framework. And we have something even more puzzling, which is, of course, the collapse of the wave function, whatever that means. And of course, this arrow here carries out the doubt, because in principle, if you have a real collapse, you don't have an evolution given by the Schrodinger equation anymore. Of course, these can lead to all sort of like ideas about interpretation of quantum mechanics or different theories within quantum mechanics. And perhaps all this confusion, which is present, perhaps all this confusion is one of the sources of why we are having troubles to talk about gravity. And in fact, when you look to this, many questions emerge. For instance, what is an observation? How come does it happen? And what really divides the framework between classical and quantum physics, right? And this is actually unprecedented in physics. This is quite terrible. I mean, that we've been in this situation for over 100 years, right? And we don't have a proper grasp of what we mean when we talk about quantum mechanics. Now, not so surprisingly, because everything is so complicated, we tend to do something when we talk about quantum mechanics. So when we teach, when we learn, when we do research on quantum mechanics, what we do usually is to take a classical system that we know how to write down Hamiltonian, for instance, and then we quantize it. So this has been the most canonical approach to actually talk about quantum mechanics. And this is also what we learn when we take a textbook on quantum mechanics. The question is, should we be doing that? Should we be starting with classical systems and looking into quantizing them? Or should we be doing something else? Perhaps we shouldn't be doing that, because if we really believe that in some sort of like weak emergence in nature, what we should expect is that there are some fundamental laws, and then out of those laws, there are some hierarchical emergent laws that should be derived from the fundamental level. And so if we truly believe that the ontology of the world is somehow quantum mechanical, maybe we should invert this whole thing and talk about classicalization, right? And so we should forget about start with classical systems and should start with quantum systems and trying to understand how we recover some classical dynamics from them. Now, you might be thinking now, okay, why should we care about that, right? Isn't this all very obvious? Well, I mean, first of all, these two different proposals of quantizing or classicalizing, it's not really a two-way street, actually. As you know, when you talk about, for instance, microphysics, you can have diversity of different theories in the micro that recover the same macro physics. And you can see that in any like effect field theory dynamics, both in quantum field theory or stat mech, for instance. So we should care about that because those two, the map is not exactly isomorphic. More than that, we know that whatever quantum gravity is, it cannot be just simply quantum general relativity. So if you take the classical theory of gravity, general relativity, and you try to quantize it, we have issues. So gravity challenges that approach that we can take a classical system and just quantize it. So we need to do somehow better. Okay, so what then? What's the alternative? And so the alternative that I want to argue in this talk is basically that one should forget basically all the classical notions, and one of them is space-time. And therefore, even the idea of having some gravitational theory being fundamental. So really, we look to quantum mechanics, and that's our fundamental framework, which means that we have a Hilbert space, we have quantum states, and we have evolution equation. And of course, everything else should come out of it. And as crazy as potentially this can be, or as ambitious as this can be, the heavy lifting has been done by a lot of people, and this is still a very active research program. Of course, we're still starting to unfold how this can be even possible. Also, it's worth mentioning that the reason why one should argue in favor of this is because from what we've been learning from trying to quantize gravity in the last, I don't know how many years, is that gravity seems to involve, first of all, a locally finite number of degrees of freedom. Also, gravity seems to be holographic, and it seems to be emergent. I mean, our best quantum gravity theory, like string theory, when we talk about ADS-CFT, probably you heard about that before. In there, we cannot even talk about, even the dimensionality of space should be a fundamental thing, because we have a theory which is dual to another theory in different number of dimensions. Yeah?
The universe is not actually the center, so I don't understand why you try to take some teaching from a theory that don't describe the universe.
Yeah, absolutely. I will skip that. I'm happy to come back to this point later if you want to. But of course, these are ways to motivating why you should think that maybe gravity or space-time should be emergent. Of course, ADS-FT cannot be the fundamental theory of the universe. In fact, not only is it de Sitter, but also in vacuum and so on and so forth. There are all sorts of things which have nothing to do with our universe. So you can use that as a motivation to maybe argue that gravity should be emergent. But whatever you do to have this emergence gravity, you shouldn't rely on the fact that you have an ADS boundary, for instance, to talk about your theory. But that's a whole conversation, of course. Anyway, so within this framework, we can talk about now some kind of like quantum first approach. And basically the research program that I'm going to be exposing to you is mostly due to Steve Giddens and Sean Carroll and collaborators. I'm going to be showing the references at different steps that you can actually check if you want to see how they are detailing the arguments. But there are basically 6 different steps. And I'm going to be trying to explain or give intuitions for each of those steps so that you can understand how we start from only a Hilbert space, and then where you have some particular quantum state and a Hamiltonian. Then you go about in factorizing this Hilbert space such that your Hamiltonian looks local. Then you can compute the mutual information between different factors in Hilbert space. Yeah, of course.
Now, certainly, I can see this as a kind of suggestive thing that maybe this is in the end finite dimensional. Certainly, it could be infinite dimensional. Even one harmonic oscillator has infinite Hilbert space dimensions.
Absolutely.
But your state could.
You don't have the same argument. Yeah, thank you. Sorry. Because the crucial thing for us here was the fact that when you include gravity, you actually have a bound in the amount of entropy that you can have for a given region, right? And so you know that whatever would be the Hilbert space associated with that region cannot be described by something that looks like as if you had an infinity Hilbert space.
I mean, I could think of a harmonic oscillator where I'm forced to have a 99% probability rate on the first 5 levels.
Sure.
Just very little bit of weight going into a tail and to infinite dimensions or so.
Yeah, but like when you talk about like I need to think more about that. But because really what we're trying to infer here is like it's the counting of degrees of freedom. It's not necessarily the counting of like what kind of states are excited.
Yeah.
Right?
I mean, there
So
are typicality arguments in thermodynamics
yeah.
that make you say, oh, it's like e to the entropy is
Exactly.
the amount of effective levels or so.
Yeah.
So then it's probably up to be understood in that sense.
I would say so, yes. Of course, maybe kind of like tuning in with this question you have, one could ask, how come actually QFT works so well, right? I mean, if you run this argument and it's a correct argument. Well, it turns out that you can compute what would be this entropy if you had, like, for instance, a black hole of size, maybe, let's say, 1 centimeter cubed. And actually, when you do that, you arrive at the dimensionality of the Hilbert space associated with a 1 cubic centimeter for a black hole is enormous, it's gigantic. So it makes sense that even though we do QFT with infinity dimension of Hilbert space, things actually run somehow smoothly. But perhaps if you approach like some regions of a black hole, then you would see problems with this this approach in which the dimensionality is taken to be infinity. Okay, so still developing on the item 1. As I said before, we're kind of like trying to ignore those complicated parts of quantum mechanics and just focus on the initial part, where you have like a state, a Hilbert space, and an evolution equation. And so, to some extent, we have a very austere quantum mechanics in the sense that we have a Hilbert space. Now we impose that the fact that the number of dimensions is finite. So I'm kind of like hinting towards the question that Chazalev asked. Well, of course, we have quantum states. The Hamiltonian gives the evolution equation, basically, encoded in the Schrodinger equation. But they also have like all the eigenvalues associated with the Hamiltonian. And in principle, that would be all. So whatever we are about to derive, everything's going to come from this simple, very minimalist quantum mechanics, right? But then you could say, like, okay, but wait. When I look to a Hamiltonian, for instance, I can give you like a Hamiltonian for a harmonic oscillator within some interactions. You might say, but we do have space here, right? I mean, space somehow already appears, at least an operator. The thing is that there is no reason for this spatial basis if you go back to the slide before, right? In this, you only have the Hamiltonian and you have a particular vector in Hilbert space. And to choose a particular basis is something that we do, but should be justified as well. So in whatever thing that we're trying to emerge space, a space should be singled out as something special, not something given by picking an arbitrary basis and making it special. And so we need to understand how or why is this basis particularly relevant for us. At the end of the day, really what one has would be in principle just the dimensionality of the Hilbert space, because you are in finite dimensional Hilbert space, and also the energy eigenvalues. And the ultimate theory or result in this kind of framework would be you start with this enormous list of numbers, and somehow you can derive the standard model of particle physics. Okay, we are far from that, right? I mean, we're going to be talking about very, very, very simple situations here. But in principle, if you really believe that quantum mechanics is the fundamental thing and there is nothing more than that, and gravity is emergent as well, everything should come from this kind of like simple description of quantum mechanics. Okay. Yeah?
When you say gravity is emergent, what do you mean?
I'm going to explain. Yeah, but it's basically following this. I'm going to be saying that you can talk about the geometry without ever imposing that you have gravity fundamentally. So you don't have gravity as an interaction. You have actually a construction of geometry. And this geometry behaves in a way that looks like GR, even though fundamentally you never had anything that looks like a spin 2 particle, for instance.
All right, but there are more degrees of freedom than the degrees of freedom that's on the molecular ground.
Fundamentally?
Whatever you're going to say.
I mean, there is no fundamental degree of freedom associated with gravity. Okay. So that has to be, that's emergent. Okay, so the second thing is, what about the factorization of Hilbert space? What do we do about that? And how we come to a preferred sort of factorization? Well, the things that we're going to see is that we the imposition of locality for the Hamiltonian picks up, in general, a unique factorization for the Hilbert space. I guess the intuition you can have is, imagine, for instance, I come to you and I give you a hydrogen atom, right? And what we do usually is to decompose that as an electron and a proton. So we have like those tensor product of 2 Hilbert spaces, and then we talk about that. Why do we do that? Why don't you have combination of degrees of freedom associated with the electron and with the proton, and then we talk about those degrees of freedom as opposed to the electron and proton? And one of the reasons is that if you try to do that, you're going to see that your Coulomb interaction that is local and very simple when you talk about electron and proton becomes highly non-local and very complicated if you decide to talk about this mix of degrees of freedom between an electron and a proton. So you see that the reason why already we can see that we choose to decompose a quantum system as an electron and a proton has to do with the fact that the interaction term looks local. And this can be formalized, actually. So there is this paper by Carroll and Side from last year. It's called Quantum Mereology. And basically a discussion of how we can pick a factorization of Hilbert space that looks both classical and also that looks local, and then you can invert the argument. You impose locality, and that picks a particular factorization. So you know the common law. You have a Hilbert space. For instance, you can divide, let's say, in 2 different factorizations. We know how to write a Hamiltonian in this particular way. So when you do that, now you can impose a few conditions to try to pick a factorization. The first one is that if you have a classical system, the wave function should behave more or less should evolve more or less classically under some equation of motion. That's not the Schrodinger equation. So and to have that, you have to impose usually 2 different things, which I guess probably people know as the Zurich sift. And basically that the localized states have to remain localized, and also that entangled states have to remain entangled. So if you have like a system and environment, for instance, after you have the measurement or the entanglement between system and environment, then there is no further entanglement, right? So you have those pointer states. The other thing is that now you can impose locality. And how does that work? So imagine that you have a Hilbert space, and you do some arbitrary factorization of Hilbert space, which can be completely random. You can choose. Well, it turns out that for an arbitrary factorization, you can always write the Hamiltonian using this factorization by summing the self and then 2-point functions, 3-point functions, where you actually make interactions between those different factorizations that you have in the Hilbert space, becoming more and more complicated. Well, it turns out that this particular series, in general, do not converge for a general factorization. Most of the time, it's very hard to even find any sort of Hamiltonian that you can write that you truncate the series at a finite k, where k here is the order or the k point function. So how do we find the right factorization? Well, you can impose now that the series should converge. And so if you impose that series should converge, then your Hamiltonian is actually a local. The series is truncated. And so by imposing that your Hamiltonian should be local, in principle, you select a given factorization. And this is a result from a few years ago by Kotler, Pennington, and Ranard. The interesting thing is that in this paper, there are a bunch of caveats, and I don't understand it completely myself. And that's why I have this asterisk here for A, because actually they say it's almost unique factorization, but it's not completely unique. There is a whole equivalent class of different factorizations that would give you the same local Hamiltonian.
So if it's finite dimensional, doesn't it have to truncate at some point? If you have finitely many.
That's a good question, actually. I'm not so sure. So,
it does. I mean,
yeah.
if you have finitely many systems, yes, of course it does.
Yeah, I will take what you're saying then, because I'm not sure. Okay. Okay, so now that we handled the structure, more or less, of the Hilbert space, let's also talk about computing mutual information between those different factors. And so, as you know, the mutual information basically is given by the entropy associated with a given factor, the sum of them minus the overlapping region associated with those two different factors. The thing which is interesting about the mutual information is that it is a scalar quantity, is also symmetric, and it's non-negative. So it already hints you at some sort of like metric structure, or at least could be used to maybe define some sort of metric in this graph that is here in Hilbert space. Moreover, there's this result from a few years ago that the mutual information actually between two different factors in Hilbert space is an upper bound for correlators. So whatever correlator that you define in this space, and you compute this basically the standard deviation of those correlators, you see that the mutual information is always constrained given an upper bound. And so this is very interesting because actually when you have the 2-point function of a given observable between those two different factors that could be localized in some a space, they usually goes or they decay with the distance separating those two factors. This is for a massive theory. If it's like actually massless, then it has a power law decay. So in principle, you can already imagine that you can actually use the mutual information as a way to encode the distance between what would be the two, what would be the distance between those two factors if you had a geometry associated with them. There's a question there, over there. Yeah? Okay, no, I don't know, yeah. Okay, from which year do you know? Yeah, okay, so yeah.
It's really old, I've seen it in really old papers. I know, but there hasn't been other papers before, right?
Yeah, I think the statement was that for every operator that you imagine there is as well.
Okay, well, that's good. Okay, so we more or less can already have the intuition that the mutual information can be used to somehow give some information about the emergent geometry if you were to embed this graph in a particular geometrical framework. Now let's be a bit more specific. There is something that I haven't told you so far, but we're talking about very non-generic quantum states. The states here that people have been considering they're called redundancy constraint. And they're kind of just a generalization of states that actually the entanglement entropy goes with the area associated with the region that you are considering. So this is actually fundamental for the conclusions that we're going to arrive later. In fact, also these redundancy constraint states, they have this property that if you were to select now some sort of coarse graining of the different factors, the entropy associated with this now different coarse grain, let's call it sigma, is given by basically the mutual information that you have between factors inside and outside that region. So for redundancy constraint states, this is an equality. Otherwise, this would be just an approximation. And the conjecture now for Carroll and Tsai is that this graph information that we've been discussing so far is enough to capture the coarse geometry of this area Loy state. So whenever you have all these properties that we just described so far, you have all the information that you need to finally start talking about the geometry. And so let's do that. So let's go forward, and now let's try to define some metric, which is going to be a function of the mutual geometry between those different factorizations. Well, yeah?
States, because you're speaking about the mutual information, but what
Yeah.
which state there? So many states in there.
Yeah, so you have to consider a class of states that they have this area law behavior, which means that if you compute the entanglement entropy for a given region, that entropy is going to scale with the area, not with the volume. So basically, you have to imagine that those states, they have to...
So Yeah, just also put these things in some space and then.
Absolutely. I'm gonna briefly mention that in two slides, actually. Yeah, so I guess the important message here is that many things that we've been discussing so far still relies on the fact that you kind of know that there is a geometry. But then you compute all those things and then you ignore the geometry, and then you have to somehow be able to recover it from another given technique. Because if I were to give you all this information without ever telling you what kind of geometry your system was embedded in, would you be able to tell me what is the geometry? And so this is what they are trying to do. So you invert the whole logic. Of course, those are still like some clutches. Like they are trying to help you how to derive those things. But ultimately, you should be able to do all of that without relying on the fact that you know some notion of geometry underlying the system. Yeah. OK, so as we saw, we in principle have some graph in Hilbert space. If you remember, sorry, going back, this picture, we have like this factorization of Hilbert space. We define some graph. There are some vertices, which are the factors. And the edges are basically defined by the mutual information among those different factors. The question is there a map that brings us from this graph in Hilbert space to what would be a graph in geometrical space? And yeah, question? Here, yeah, so imagine that you have a big Hilbert space, and then you do some factorization following what we discussed before, and then you have all those different factors, and now you compute the mutual information between every two factors, and this mutual information is actually what's giving you the edge connecting those different factors. In this graph, the mutual information gives you the weight between those different factors. And when you want to use this mutual information in the edge here to actually give you a notion of metric now in this particular graph. So how do we do that? There are a bunch of assumptions here. So it's not even clear that you can actually do this mapping. So you assume that actually you can do it, first of all. And you assume a very simplified version of the graph, right? Because in principle, what you had vertices in the Hilbert space, now the vertices in the geometrical space could be something completely more complicated. But you assume that they all remain the same. So actually, the only thing that we do is really to change sorry, and here the tilde should be, oh no, sorry, it's correct. So the only thing that you do is assuming that the edge connecting those different factors, they are changed. So the weight before was given by the mutual information, but now we change. We say that the weight between those two different factors, P and Q, is given by this relation. So of course, if P and Q are equal, there is no weight, which is basically to say that mutual information is 0, and also the distance between you and yourself is 0. But if they are different, you introduce some distance scale, which here is LRC because we have this redundancy constraint kind of state. And you have this phi mapping, which is a function of your mutual information that you computed before. Here you have some normalization I0, just to guarantee that this argument here is between 0 and 1. Okay. Now, what are the properties that we expect from this particular phi map? Well, the intuition is the following, and we know this from QFT in vacuum. So if you have a QFT and you have vacuum, and you factorize the Hilbert space, you know that nearby regions, they are very entangled, and regions which are far away, they are not very entangled. So we know that from just normal QFT and computing entanglement for the vacuum, for instance. So we have the notion that things which are more entangled, they are close together, okay? So using that intuition, you can actually derive some properties for the mapping. You know that the argument runs between 0 and 1. 1 is when you have like maximally entropic states, or sorry, maximally entanglement entropy between those factors. And then you assign some 0 distance to that. And when there is no mutual information between those different factors, they are in principle infinitely far away from each other. One example of this mapping would be to take minus the log. That would have the same the right properties for this function, which is also, of course, monotonically decreasing. Yeah, so with that, we can finally then talk about some sort of definition of distance. So imagine that I have two different factors, and they are all connected by some intermediary factors. The distance between any two factors is given by the minimal path that you take in your graph. And the reason why you take the minimum is because when you take this definition, then you also satisfy the triangle inequality. So now you are arriving finally at some metric notion. It is positive, the distance, it is symmetric, it is a scalar, and you have the triangle inequality. Yeah?
So I find this very fascinating. Let me just ask you about
Yeah.
the conceptual puzzle here.
Mhm.
So we think typically that we can actually operationally measure the distance between two events.
Yeah.
So we can think of putting a ruler there or
Yeah.
doing some more refined experiment and get an actual value. For every single run we do this.
Yeah.
But mutual information of these other entropic quantities that we have in ADCFT, they are not measurable. So
Mhm.
they are not observables. And
Mhm.
you need, in principle, many copies of a quantum state if you need to experimentally determine the mutual information, for example.
Mhm.
So it seems that somehow there's a clash that you want to define an operational notion that you can really determine in every single run by another notion that's not of that form.
Mhm.
So I wonder how that is seen or treated.
I don't think it's treated at all. I mean, I think people are even far to talk about that, right? Because to some extent, you're bringing the notion that you can go and measure something, right? And I mean, we haven't even touched upon the fact that you have to discuss measurement here. So like you know that in principle, the mutual information, as we discussed before, can be related, at least as an upper bound, to correlators that encode the notions of distance. So we know that. And even when I write a two-point function, we're not talking about measuring anything, right? It's just a two-point function. Now, to talk about what you're saying in particular, it seems like way further ahead of even what we discussed here. Because I cannot even think of what it would mean to actually bring a ruler or anything that can be measured in terms of distance in this framework, right?
Fair enough, but maybe you don't even need this. No, I mean, if you have, say, quantum states in your theory, they are not orthogonal.
Mhm.
And it doesn't matter what kind of measurement theory you put up with, you will never be able to distinguish them.
Right.
So you can argue on a kind of a very basic level what's possible or not possible.
Yeah.
I think it would be interesting. I mean, not saying it's impossible or this
Yeah.
kind of kills the idea. I think it would be very interesting to see how it could come about here.
Yeah.
You obtain quantities that are more measurable from one that are not.
Yeah, I completely agree. I haven't seen anyone having this discussion so far within this program, so I think it's an avenue that someone could think more about it, for sure. Anyhow, so we arrived at this definition of distance. And so we can, of course, now, I mean, we so far, like having a distance between two different factors doesn't tell me much. In particular, doesn't tell me if there is even a smooth geometry associated with this, or what would be the topological properties such as the dimensionality of this geometry, right? So we finally go to item 5, which is how do we reconstruct those smooth geometries? And so the idea here, first of all, is to ask, is the geometry that you have resulting from this kind of algorithm even smooth in first place? And so the idea that they propose is, for instance, you go back to the Hilbert space, and you use the metric that we just defined to consider some region around a given factor P, and you compute the entropy associated with the state within this region, okay? As we saw before, the entropy of those states, they scale usually with the area. So you have this scaling with this R, which is the size of the ball, basically. But because we don't know so far if this is a proper geometric space or not, if it can be embedded in some geometry, we so far only have the graph in the Hilbert space. So the scaling is going to be given by some number that we don't know what it is. And actually, this is actually some fractal scaling, because you just have a graph structure. It turns out that if this number is actually an integer, then you can say that there is a geometry in which you can embed this graph such that the geometry dimensionality is going to be given by this integer df plus 1. And plus 1 because, in principle, this would be scaling as an area if you had that kind of a state that we discussed before. In particular, you can also define now the notion of area. I'm not going to go into that just because we're going to use it later. But you can talk about the area associated with this particular region, also defined in terms of the mutual information. OK, so in principle, if things work out fine and you have a smooth geometry and you have some given dimension, the question is, how do you recover what's going to be the geometry? And so there is one particular technique that is in the seminal paper by Carroll, Kao, and Michalakis, which is called the multidimensional scaling. And I'm skipping all the details, and I'm just going to show you the things that they do. And so they run the whole algorithm for 2 examples. One of them is the 1D antiferromagnetic Heisenberg chain. So what you have to imagine is the following. You know that this system is a quantum system is in 1D, but forget about that. So I just come to you and I give you a quantum state. And I never tell you what this is about. And then you run the whole algorithm. And then you use this MDS, multidimensional scaling, to try to infer what would be the corresponding geometry. And what they recover, like through this MDS, you can build a matrix which has to do with the coordinates associated with the system. And then when you plot the values of the matrix for a given coarse graining that they consider, they get this plot, which is roughly one-dimensional. And then when they do the same thing for another system, which is the coarse grain 2D toric, sorry, there's a typo here, toric code, they also recover some 2D geometry, even though you only have initially the quantum state. For those two systems, the quantum state is actually the ground state for both systems.
And in this case, you tell what the systems are, right? These are ordering of the systems.
You're given the quantum state, and then you do the whole approach that I just described, without knowing the geometry in which those systems would be living in.
If I give you a pure state, of course, you can find a transformation that, of course, global transformation maps everything into the 0, 0, 0, 0, 0 state, right? I mean, so in which case, of course, you're not going to be able to.
I'm not sure if I understand your point, actually.
All pure states are the same. All pure states, I mean, when you usually see the modulo unitary transformations are the same. You cannot distinguish if I give you a 2D system or a 1D system. They're the same. I can make a transformation that gives exactly the same thing.
But you give them the state and the Hamiltonian.
Yeah.
You give it a Hamiltonian. Okay.
Of course. And yeah, I'm running out of time, so let me quickly cover the last point, which is going to be just some general intuition. So we kind of understand that, of course, if you change the quantum state, we are like also changing the entropy and the mutual information, and therefore we're changing the geometry. But how is that connected with the energy, or like actually the matter content of the system? Because that's what we have in Einstein's equation, right? And for that, you can rely on something called the entanglement first law, which in the context of QFT has been discussed by these folks a few years ago. And there, what you do, you define some modular Hamiltonian, which basically you take the density matrix and you take the log of it minus, and you have this modular Hamiltonian. And then if you take the relative entropy between two different particular quantum states, it can be written like that. But it turns out that if you have just a small perturbation between those two quantum states, to linear order, the relative entropy is actually 0. And so you arrive that actually the variation of the VEV of the modular Hamiltonian is given by actually the variation of the entropy. Now, it turns out quite surprisingly that it's being shown, at least in the context of some conformal field theories, that the modular Hamiltonian is actually connected, or you can recover in the IR limit actually what would be the corresponding stress energy tensor for the 0,0 component. Of course, it's the energy density, basically. And so now we saw that not only we had before the entropy being used to define what would be the geometry, but also now we see that by using the variation of the state, you have this variation of the modular Hamiltonian connected to the T00 component of the EM tensor. So our final, basically, summary of what has happened is that we had some sort of like notion of connecting some variations in area or distance with the variance of entropy, and then you have this notion of like emergent space as it was defined here. If you know the variations of area for a given perturbation and you do a lot of math, you can actually recover what would be the corresponding curvature associated with that variation, and then you can also derive what would be the Einstein tensor. But then if you run now the other side here and you use the entanglement first law, and you take this IR limit, at least in the context of CFTs, you can actually connect the G00 of Einstein's equations to the T00 of those given theories. And of course, this is not enough. I mean, I haven't talked about time, I haven't talked about Lorentz symmetry or anything like that. But if you could now also work out what would be having the Lorentz symmetry in this framework, then you can do a boost transformation, for instance, and recover the full covariant Einstein equation. Of course, people are still not there. And that's why there is still a lot of work to do. And when I was coming here, first I was like, I'm going to put this figure here because we want you. We want your help to also keep working on this. But then I went to the kitchen and I saw this communist propaganda. So I decided to change, and maybe this is going to be more appealing for the group here. So there's a lot of work. First thing is we can still keep exploring this geometry from entanglement. Forget about gravity. Even if you have or not gravity, only thinking about simple quantum systems and the kind of geometry that they would be associated with, this is an interesting question on its own, okay? The other thing is how we recover the Lorentz symmetry. You see that time here was completely taking a special role. It had the Hamiltonian, you had the time variable from the very beginning. So everything here was like deriving or trying to recover some spatial geometry. But we should be able to somehow talk indistinctly between time and space if you want to recover proper GR or what we have in like even underlying QFT. So there are many questions about that. In particular, moreover, you know that if you have a finite-dimensional Hilbert space as opposed to an infinite-dimensional Hilbert space, you don't have the same representation of the Lorentz group. You have problems with that as well. So the question of also recovering the continuum limit of the infinite dimensionality of Hilbert space that we're used to from this framework is also very complicated. Finally, the directions that I am interested right now, so I'm trying to start working with 3 last items. The first one is, can we talk about time actually being emergent in this framework? So instead of like having that time evolution given by the Hamiltonian, maybe talking about some thermal time hypothesis. And you know that this paper by Cohns and Rovelli from actually quite a few years ago, where instead of considering just like pure states, you talk about also having mixed states, and you can define a time variable which is going to be emergent. There is also the problem of like, how do you recover diffeomorphism, right? I mean, that's a whole another business, because if time is fundamental in this framework and you have a foliation, as you mentioned before, then you have a preferred gauge, basically. So diffeomorphism would be actually an emergent symmetry of the theory. And then you can try to find what would be the hints that the emergent theory would be diffeomorphic. And we don't know that. Finally, maybe honoring my background in cosmology, I'm actually interested in much simpler systems, like what would be like the FRW geometries. So I just want to do the full background cosmology without perturbations. I would expect that to be somehow simpler and more manageable to tackle. And also specific cosmological backgrounds. As someone mentioned before, can we, for instance, recover the Sitter geometry as opposed to just like those flat, simple examples? Because that would be also very interesting, as we know that most theories that are like quantum gravity that we have nowadays, such as string theory, they have a bunch of issues recovering the Sitter space. Anyways, that's kind of like all I got. So thank you very much. I'm happy to take questions. Yeah.
First, thanks for the nice talk.
Okay.
It was really interesting.
Welcome.
I would like to maybe reconnect a bit with the question that Marius asked before.
Mm-hmm.
About I don't know, because if I to think about also some other attempts to do the same thing, like the quantum server automata.
Mm-hmm.
I've done similar things, but in the end, if I'm really intention to retrieve somehow a notion of gravitational interaction, I mean, I think that, what do you think? You need some more extra structure, more information, like something that could relate like the topology of the network with the dynamical evolution of the described system. Because, I mean, so far, I can say, okay, I have my network of systems, and I have my dynamical evolution, which may define some symmetries, maybe of the emergent dynamics, but emergent geometry. But there's no notion of dynamical geometry, no?
Mm-hmm.
If I want to think something about in the direction of general relativity, I think there's probably something missing, no? Something that could relate really the topology of the network of your interacting system with the system itself somehow.
Yeah, I mean, I'm not sure if
there are also some proposal where they define really this notion of dynamical network structures, where there's a sort of evolution also of the network network where maybe some new edges can be created, something like this.
Yeah, I mean,
You have some.
so we don't have anything like that here, right? Like we don't have dynamics basically, right? There is so the emergent geometry has no time.
But
Like
you have a notion of Hamiltonian, no?
you have in the original the quantum in your Hilbert space you have this Hamiltonian, right? But in the resulting geometry, in principle, everything is static. Like really, what happens to have that sort of dynamics here imposed by hand is that you're perturbing your quantum state, and that's perturbing your resulting geometry. But that's given by hand. It's not as if you were in this framework really having a dynamics of your quantum state such that you result in perturbations in your resulting geometry. So you're very far. We're very far from that, actually. You know. Yeah.
So first of all, I missed the first part of the talk because I was trying to watch it from YouTube, but I was obviously waiting out. So if you already mentioned this, sorry. So first a question: have you made a connection with loop quantum gravity?
Okay.
In what you have said or not?
No, so not trivially at least, right? So it could be the case that it could even be connected with string theory potentially, right? We don't know. But the thing is that different than loop quantum gravity or string theory, we're not introducing any particular different fancy degrees of freedom that when quantized could recover something like classical gravity in a given limit, right? So in principle, there is no notion of there is no notion of geometry or gravity fundamentally. You just have like quantum systems that somehow, by themselves, you do a sort of coarse graining from which you recover the geometry associated with those systems. There is no fundamental degree of freedom associated with, like there is no spin 2 graviton per se, you know.
Look,
yeah.
When you were saying it in the beginning, I was like, okay, I'm not gonna like that. To be honest, it's just for you. I think you would be interested to see this work. I think you're saying exactly the same thing.
Okay.
As the program of a junior behind the program now. The so-called squeezed states of loop quantum gravity, where what you have is graphs. The nodes are basically Hilbert spaces, and you encode distance, and generally speaking, space-time geometry by the correlations. And they also use exactly this notion of neutral information to estimate the values. And I mean, look, you look on gravity, there is no speed to gravity. You recover 0.2 fraction of Hilbert amplitudes that tells you that there is going to be something like that in the limit. In a limit. Fundamentally, you just have a bunch of degrees of freedom. So long as you have a Hilbert space, which is some sort of quantum degrees of freedom, that is not different at all from gravity.
But maybe I can ask.
There is a story on how you get that specific kinematical space and how you get dynamics, which you don't have, but that can actually be together.
Maybe I can ask you a question then, because of the whole point of quantum gravity is to have loops, right? So I guess you're introduced somehow some particular quantum system in which you have those loops such that you recover the classical gravity, right?
Loops is a mathematical technique.
Okay.
Wilson loop. It doesn't really mean anything. It's one basis.
Okay.
Another basis is networks. Another basis is the squeezed state basis. I didn't see a contradiction.
Yeah.
Group together. I understand it's a different approach. But
I would be happy to talk more about that. Yeah, if you have time at some point.
I can point you to.
Yeah, that'd be perfect. Thank you. Yeah.
One more thing.
Yeah, of course.
I wonder how quantum theory plays in here. So, because you mentioned the following. So, I mentioned classical physics. I give you a classical Hamiltonian function, and then a classical, say, statistical mechanics state that describes a probability distribution of the kind that we expect. Where we also expect that particles that are close by are somehow strongly correlated with the ones that have flown far apart. So, I could in principle imagine doing the same thing. I could try to map out the correlations and from that define some distance, and then if I'm happy, then perhaps even reconstruct the underlying space.
Yeah.
Is there, perhaps it would be compelling somehow if you could say that this program really only works when you start quantumly Is there hope to do that? Because is there, for example, in the notion of mutual information, some way for that? You say the way that mutual information behaves and gives rise to geometry here is something you couldn't have classically. Yes, it's entanglement entropy.
Yeah, I would be inclined to say so, and I think there are other things, right? I mean, there are many things that I haven't discussed here. For instance, right? You could ask the question, what happens with a EPR pair, for instance? If you, because everything I discussed here so far was pretty much implicitly in the ground state. But what happens when I have excited states? If I have a Bell pair, for instance. And so this kind of framework somehow recovers some notion of EPR equals ER, right? So we saw before that the notion of this weight that gives the distance in the emergent geometry, the weight would be equals to 0 if the two factors were maximally entangled, for instance. And so this is a hint of like trying to somehow recover the EPR equals ER in this framework. So you would have, of course, you don't see the ultimate geometry. You don't see that there is some sort of like wormhole or anything. But by construction, you associate a 0 distance between those two factorizations. So I think there are a bunch of elements, and of course here I'm presenting the big picture. But when you read the papers, I think there's so many different things that are relevant for only in quantum mechanics that I guess you cannot do the same in just stat mech, for instance, as you were saying. In particular, the very last point where of course, talking about geometry and distances you can do for correlators, but then associating that with the content of the matter content or energy content to recover the Einstein equation, kind of towards the end, you're really using like this notion of the first entanglement law, for instance, which is, as far as I know, like a purely quantum mechanical thing.
But Jacobson's paper originally can also be read classically.
Oh yeah, but in Jacobson's papers, you never say what is the entropy, right? So you of course you say that there is this entropy, and then you can associate with the area and everything, but you don't say where that's coming from, and you also don't derive what it would be like the laws that he's imposing would be just the classical entropy laws, not coming from like the entanglement entropy as we kind of like argue here. But for absolutely all those different papers or proposals, they are overlapping considerably, I think, and I guess people are trying to do different realizations of them, but they, to some extent, they converge a lot. Yeah. Yeah. Welcome. Yeah.
I think you mentioned at the end that there's a problem to recover in string theory, for instance, like specific cosmological backgrounds.
Yeah.
I remember that like a couple of years ago there was a paper that string theory cannot explain a positive cosmological constant.
Yeah.
Do you know a little bit about the developments there?
This is like a very active debate, and people were very, very strongly opinionated about it. I'm very biased on this discussion, and my bias is to say that, as far as I know, there is no clear realization of having a positive cosmological constant in coming from string theory. But there is a whole other camp that would strongly disagree with that, and this is people who have been arguing that you can actually embed inflation, for instance, in the early universe in string theory, and then you have a quasi-de Sitter-like expansion. But I think the question is far from being settled. Yeah, for sure.